Welcome to sections 4.8 and 4.9, the conclusion of chapter 4, our introduction to vector spaces. In these sections, we're going to be looking at a few types of vector spaces that we can encounter when working with matrices in particular, and these are the row space, the column space, and we'll also be looking at the null space again, and then seeing how all of this relates through the rank nullity theorem. So we're going to consider an M by N matrix A, and we're going to look at three different types of subspaces. So first off, of course, we have the null space. So the null space of A is going to be the vector x, which is an element of Rn, such that A times x equals the 0 vectors. So if you recall, x is the solution set to this homogeneous system of equations, right? If we have this system all equal to zeros, x is the solution set for that system. This is a subspace of Rn. We have proven this in the past. The dimension of the null space of A gets a special name. This is called the nullity of A. So the dimension of the null space is called the nullity. So for example, if we take this matrix here, without going into all of the details of the ERO row reduction, this matrix, when put into row echelon form, gives us a 1, 2, 6, a 0, 1, 2, and then 2 rows of all zeros. So we get our pivots right there. We do have a free variable in this matrix, so that would be x3. We would let it be t, which is a free variable. x2 then, x2 plus 2t would be equal to 0 if we're looking at the null space. So that would be solve negative 2t, and x1 minus 4t plus 6t, so that's plus 2t. And then subtract that over, so we get minus 2t again. So for this matrix, so the null space of this matrix A, so it has the form negative 2t, negative 2t, t. And if we go ahead and bust out that variable, so we put t out here, we have negative 2, negative 2, 1. And this is going to be the span of the vector negative 2, negative 2, 1. So in other words, right, any linear combination of this vector, so any multiple of this vector, results in an element of the null space of A. It is a solution set to this system of equations when set all equal to zeros. So if this is the null space, notice there is only one vector here, right? And this would form like the basis. So the nullity of A, in this case, there's only one vector, so the nullity of A would just be 1. That is the dimension of the null space of this matrix. So if we're trying to identify the nullity in general, we can look at, so dimension of the null space is the nullity. We can also look at the number of free variables in the linear system. So notice here, right, the null space is formed using these vectors with the variables within them, the free variables. We bust those out, and for every free variable, we would get a different vector. So if this was like an r, an s, and a t, we would get one vector for r, one for s, one for t. Okay, so but the number of free variables gives us the number of vectors in the null space, which gives us the nullity. And of course, the free variables correspond to the number of unpivoted columns in row echelon form of A. So if we put this in row echelon form, we look for the number of free variables or the number of unpivoted columns, and that can tell us the nullity without actually having to find the null space or the basis for the null space. Now, the next type of subspace that we're going to look at is the row space. So the row space is the span of all of the row vectors of A. So you take all of the row vectors of A and then you span those. So any vector that can be created by a linear combination of the rows of a matrix, anything that can be created by that is an element of the row space. And this is a subspace of Rn. Okay, so just like the null space, it's based on the size, right, the length of the rows, right, or the number of columns, if you want to think about it that way. Like with this matrix, right, this row has 3 elements in it, so this would be a subspace of R3, something like that. The dimension of the row space is called the rank of A. And yes, that is going to be the same concept as the rank of a matrix. So this is a concept that we're already a little bit familiar with. We're just kind of recontextualizing it a little bit here. So if we want to get the row space itself, all we need to do is take the span of all of the row vectors, right? So we just take all the rows and then span them. If we want to get a basis for the row space of A, we need to reduce A to row echelon form and then take all of the non-zero rows of that row echelon form of A, and these form the basis for the row space. So for example, with this matrix, this is the same matrix as above, so just to save a little bit of work here, we already know what this is in row echelon form. Now, the row space itself, so the row space of A, row space itself doesn't care about any of that. The row space itself is based off of the original matrix, and that will be the span of all of the row vectors. So 1, 2, 6, 2, 1, 6, 0, 1, 2, and 1, 0, 2. But the basis consists of only the non-zero rows in row echelon form. So for the basis, we look at row echelon form. We get rid of any non-zero rows and only take, we get rid of the all zero rows and we only take the non-zeros. So this is going to be 1, 2, 6 and 0, 1, 2. So our basis here contains 2 vectors instead of 4. Okay, so these vectors here, right, we would be able to span with them, but they actually are LD in this current form. And by row reducing, we eliminate those linear dependencies as we put it into the basis. So in this case, the rank of A is the number of vectors in the basis, right? That's the dimension of the row space. So that is 2. So, and the same idea here. Dimension of the row space is the rank of A. This corresponds to the number of leading variables, so not free variables, but the leading variables, which corresponds to the number of pivots in row echelon form. Right, and we always said that the rank of a matrix was the number of pivots, right, or leading variables. So if we take these two concepts together, right, we've been looking at the same matrix so far, we found that the nullity, the dimension of the null space, was based off of the number of free variables or unpivoted columns. The dimension of the row space, or the rank, is based off of the number of leading variables or number of pivoted columns in row echelon form. Now, every column in a matrix is either going to be pivoted or unpivoted. There is no alternative option. It has a pivot or it doesn't. So bearing that in mind, the rank of A plus the nullity of A equals n, the number of columns in A. And this relationship defines the rank nullity theorem. So the rank nullity theorem says that the rank of A plus the nullity of A equals n, the number of columns in A, right? Because the rank is the number of pivoted columns. The nullity is the number of unpivoted columns. So you take all the pivots plus all the non-pivots. That adds up to the total number of rows, because again, every row either has a pivot or it doesn't. For an example like this, what is the nullity of this matrix? Well, we can do this without actually even really solving anything. So notice there's a pivot right here, and these two rows are going to be exact multiples of the first one. So those are going to become all 0 rows. So we can clearly see that the rank of A is 1, and the number of columns is 6. So, by rank nullity, 1 plus nullity of A equals 6, which gives us, through basic arithmetic, that the nullity of A is 5. So here we had an example where, in order to find the nullity directly, you would have to row reduce the matrix, solve for the null space of the matrix. That would end up giving you 5 free variables. You would bust out those variables to create 5 vectors, and then span those vectors to get the null space, and then see, oh, there's 5 vectors, so the dimension is 5, so the nullity is 5. Or we can just look at the rank nullity theorem and say, well, the rank is fairly intuitive here because we know there's a pivot here and everything else is an exact multiple. So if the rank is 1 and the number of columns is 6, we can just solve via subtraction to get the nullity without ever having to actually find the null space. Now, the last subspace that we're going to look at is the column space, which is often abbreviated the col space. Okay, so the column space of the matrix A is the span of all of the column vectors of A. This is a subspace of Rm. Okay, so now we're going based off of the size of the columns. Okay, so again, with this matrix, right, the row space was a subspace of R3. The column space will be a subspace of R4, because there's 4 components in each column, right? It corresponds to the number of rows, right? So to get a basis for the column space, we still reduce A to row echelon form. We then take the non-zero columns, and this is an important distinction. We take the non-zero columns of the original matrix corresponding to the pivots in row echelon form of A, and these form the basis for the column space. So with the row space, like we saw on the last page, we row reduce it and then just take all the non-zero rows that are left. For the column space, to get the basis, we're going to take all of the non-zero columns of the original matrix that correspond to the pivots in row echelon form. So we still row reduce, we find the pivots, but then we don't take those reduced vectors, we go back and find the original vectors that correspond to them. So for this same example that we've been working with here, so we get 1, 2, 6, 0, 1, 2, and our all 0 rows. We've got our pivots here. Now, the column space itself is just all of these original vectors. And you'll see as we go through with vectors like this, notationally, we want to denote and kind of signify that these are column vectors and that this is their specific direction going vertically like this. And so oftentimes we will write the vectors in this column form. So you'll see the vector 1, 2, 0, 1, 2, 1, 1, 0, and 6, 6, 2, 2. So we like to write the vectors vertically because they are column vectors to help kind of distinguish them from, say, a row vector. Now, that's the column space itself, is the span of all of these column vectors. The basis for the column space is going to be, we're going to take all of the pivoted columns in row echelon form, so that's the first two columns, and go back and take the original columns that correspond to those. So that's going to be the first one, 1, 2, 0, 1, and the second one, 2, 1, 1, 0. And this would be the basis for our column space for this matrix. Okay, so again, there was a linear dependency here with this third one that we can then eliminate, and we're just left with the original two. We already know the dimension of the column space is the rank, and the dimension of the row space is the rank. It's all about which rows or columns have pivots in them. And so the rank of A here is still 2, just like it was when we looked at the row space. Okay, but this is another way that we can determine rank using the column space. So using all of these facts together, we can go ahead and make some amendments to our invertible matrix theorem. So it's been a little bit since we've added any updates to this. But last time we looked at it, we found that the determinant of A being non-zero was equivalent to a matrix being invertible. We have a bunch of additions now. We've got H through P that we can add on here. So the nullity of A being 0, so the dimension of the null space being 0, is equivalent to a matrix being invertible. Okay, the null space being the 0 vector, so being the only solution to that homogeneous system of equations is to make the solutions 0. Okay, to say that the columns of A are Li is equivalent, saying that the call space is all of Rn. In other words, it spans all of Rn. Saying that the columns of A form a basis for Rn. So these are these are all, of course, equivalent statements to each other as well. But all of these things can imply invertibility in a matrix if the rows of A are Li, or in other words, the row space is Rn, and the rows of A form a basis for Rn. So if we say that vectors are Li, that they span all of Rn, that means they form a basis for Rn, right? That's how we define a basis. Same thing for the columns up here. And the transpose of a matrix is invertible if and only if the original matrix is invertible. That also can be justified using the concept of rows and columns and the number of pivoted elements within the matrix. So, but all of these new ideas that we've looked at in the past few sections are equivalent to a matrix being invertible. So if a matrix is invertible, all of these things will be true about it. Or if any of these things are true, all of the others will be true simultaneously, and the matrix will be invertible. But that brings us to the end of this section and to the end of Chapter 4.